Dehumidifier, which is essentially an air conditioner, many of the same components, the main one being the compressor, which is not turning on this unit. However, it doesn't necessarily mean that the compressor itself is damaged. There's control circuitry, there's a capacitor that needs to function, and we can test these components individually. So let's talk about the compressor. A compressor is a type of motor, and therefore it's the part that we have access to through these wires, are the windings that create the magnetic field that make it rotate. Now, the windings, we don't know exactly how much resistance they should have. However, we know that they should be connected to each other inside, since a windings, they're a continuous piece of copper. So what we will do is put our meter into ohms mode and then trace back both of these wires to an easy place to connect them. And then we want to remove those points from the rest of the circuitry, because say for example that the winding inside the compressor is broken, but you still have the wires connected here, there might be some other path of current through something or another that would give you an ohms reading when it's actually not the path of current through the compressor, which would be a false reading. So we just need to disconnect one of them. Make sure that you safely discharge the capacitor before getting anywhere near it. In this case, I've already done that. A capacitor of this size can store a tremendous amount of energy, and if you touched it while it was fully charged, it could severely hurt you or kill you. I'll trace back both of these wires. This one's easy, the white wire. The second one comes through the back of the plastic box and to the top of this relay. I've already disconnected one side. I don't have to disconnect the second one. In fact, that will be easier for me so I don't have to hold it with my other hand. So let's see what the meter says. 6.3 ohms. Again, I don't know what the manufacturer rating is, so I can't tell you if that's 50% of or 100% of the correct resistance, but I can tell you those windings are connected in there, and if we apply power, it will generate some kind of magnetic field. Also, I think that 6.3 would be a reasonable number. It's a pretty low resistance, which I would expect for a higher amperage motor. But all this tells us is that the windings are not broken, disconnected. I forgot to mention, this also tells us that the thermal switch, which just about any of these motors is going to have, is operating correctly. A thermal switch is supposed to disconnect whenever the temperature exceeds a certain set point. Now, if the thermal switch goes bad, it burns up, physically breaks, then even if the windings are intact, then the thermal switch will still read and open. But because we read 6.3 ohms, that means that the thermal switch is connecting. I'm going to reconnect our compressor to the capacitor, but before I do that, I'm just going to verify, even though I know it was discharged, I don't want to lose track of what I'm doing and forget if I lose focus, so we're going to be safe. Next step, we will bypass the electronic control board and power up the compressor manually. And I know that this is safe because I see that the rating on the compressor is 115 volt, 60 hertz. And I'm not going to run it for very long just to see if it will start. Now there's a lot of components on this board, but you'll see that the red wire from the compressor goes straight to the top of this relay. So, and the other side of the relay goes to the brown wire, which comes back up here. And this black wire, that's hot, directly from the plug, okay? And that means that if we bypass the relay, it will act as if the control board had signaled the relay to turn the compressor on. In the next step, we're going to bypass the electronic control board and just make a circuit out of the compressor, the capacitor, which is required to start the compressor. And that'll be it. So you'll see that the red wire from the compressor goes to the top of this relay, and then the brown wire from the other side of the relay comes back up here and connects directly to live. All right, so whenever the relay turns on, the live or hot goes straight into the compressor. So what I'll do is put this little jumper between hot and the input to the windings of the compressor. So that way, regardless of whether the relay is on or off or working or not working, the compressor will be commanded to turn on, or it'll receive power. So I'm going to plug it in only for a few seconds. If I don't hear anything, I'll assume that the coils are heating up and that the compressor is seized because I know it's receiving power. If I do hear it spin, then that will be great. So here it comes. So that sure sounds like a healthy compressor to me, and if I let it run for a few seconds, I could even feel that it's getting cold back here, which is excellent. So that means that the compressor is healthy to every indication that I have. Also, that makes me pretty suspicious of this relay. Either the relay or the circuit that's supposed to make the relay turn on is not working. So I'm going to start working on the circuit board. Before I do that, I'll get that guy. Now before I take this board off, I'm going to tap it, tap the relay. And that's because I've had relays seize on the inside. The contactor that's supposed to move back and forth doesn't, and tapping it can dislodge it. And we'll plug this in. So discharge capacitor again. And now we know that we're just gonna have to take this board off and do some more aggressive testing on the relay. Well, even at this point in the game, a relay is a lot cheaper than a compressor, so I hope that it's just a relay. Now at this point, it's possible that the transformer could be bad. I don't know if this board is receiving any power, but we'll check the winding on the relay. So you can see, these are the contacts of the relay coil. Measuring them shows 157 ohms. Perfect. Again, I don't know the manufacturer rating, but I do know that that winding is not broken. I could, though, what probably is given, can't see it on camera, but right about there we see 12 volts. For those who may be curious, this chip right here, see the part number, ULN2003, kind of a common one, is a Darlington transistor array. That is, it's 7 Darlington transistors lined up one by one. A transistor is sort of like a miniature relay, a solid state relay, and it would allow a very small signal, like a little button or switch, to get amplified into a larger signal that can turn one of the relays on and off. So I've got a little wallboard adapter set to 12 volts DC, and I've traced back from the rectifier this pin, which is plus 12. You can see because of the stripe on the diode, which the diode's actually on the other side there, but the symbol back here shows me that this is the positive side of the diode directly from the transformer, so I know that that's positive, and I see that that goes straight to this pin on the relay coil. Alright, and that means that this pin, the other side, is the negative side of the relay coil. So just touch it. Beautiful. Now I will say the first time I touched it, I did not hear the relay click actually, and it sparked a little bit. And I think that the relay coil was not engaging initially, and I may have broken it loose by putting voltage across it. And what that tells me is the relay may have sort of been good the whole time, but then something else downstream broke that stopped providing voltage to the relay, and over time of not being used, it may have sort of seized just did enough. Whenever I zapped it, it started going again. So, and I did plug it in after that, and it still doesn't work. So the problem was not the relay. The relay is good. The next thing to check is the other side of this, which is just the output of the transformer. Now we've got two pairs of wires going to the transformer. One's red, one's white. Now the difference is one side is the primary windings and the other side is the secondary windings. Now I know that the white wires are the secondary windings because I see that they go straight to the bridge rectifier and from the bridge through to the rest of the components. The secondary side is the low voltage output side of the transformer. That's why we see them going to the rest of these components. The primary side is the input. All it goes to is the neutral pin here, and we should also see a connection to live, which I think will come through the bottom of this coil. And if we can trace this back, that's this pad here, and then here to the fuse, which that's the fuse. We'll have to make a mental note to check the fuse from the fuse to this connector. So yeah, this top red wire, that's your live. The bottom red wire, that's your neutral. And what I'm gonna do is not touch the primary side because that's gonna be high voltage. I could check that with my meter, but I prefer to tap onto the low voltage side. This should be, it's not gonna be exactly 12 volts AC, but it will be sort of around there. With everything unplugged and in the ohms mode, I'm measuring the resistance of the secondary windings. 2.4 ohms sounds kind of low because it might be okay. That is what volts mode is for. Alright, so I plug that thing in and it comes down to 12.8 volts AC. So that looks pretty healthy to me. Before I go back in, so I pulled the cover off the fuse and just checked the ohms on this, and I'm getting 0. I also see that it looks fine. The relay is fine, the transformer is fine, the fuse is fine. Right now I'm suspecting that ULN2003, those transistors in there. Well, those are the steps that you can take to diagnose or test a compressor.